Okay, welcome Milagros and Casey and Susie, and those who are watching this as an YouTube archive webinar. Thanks for coming. The plan today is I'm going to go over any questions you have about the project. This is our last webinar before the project is due. And then after that, we're going to get into Chapter 7. Chapter 7 is a really important one. It's called the Central Limit Theorem. And it's pretty much how we're going to base a lot of what we do for the rest of the class based on the Central Limit Theorem. It's also, I want to warn you, it can be really confusing for people. So I'll do my best to try and explain it, but it is a little confusing. So let me ask you, do you have any questions about the project or anything else?
We were wondering if there was any format or a specific format that you wanted us to do the project in.
Obviously type to hopefully you believe that, right? You could use definitely some kind of word processor, you know, whether it's Word or Google Docs or whatever works for you, that's fine. Double space is best so that I can put comments in. Otherwise, there's no room for comments. And the other thing is to make sure that you copy and paste the spreadsheet results. That's an absolute requirement. And that could be at the end of the paper. It could be where you talk about it, but it has to be literally copied and pasted in there. Does that make sense? Does that answer your question, or is that what you were looking for?
Yeah, that's good. Thank you.
Yeah, so I'm not that picky on format. What I really care about is that your writing is clear. You know, you should check for grammar mistakes, and that it's readable, and especially that you are putting in for every statistic and every chart recommendations to your client on what decisions are going to be made after seeing that chart or that statistic. Does that make sense?
Yes.
So more than just defining it or saying, hey, the mean was big. That's not really a recommendation. Does that make sense? So that's more important as content. Okay, but that's a good question. So I'm not that picky on that. And of course, I want you to make sure that you use statistical vocabulary as much as possible, since this is a stats class. Any other questions? Any other questions? Okay, I'll also take questions at the end as always, but if you have them throughout, you can always ask. One of the things I like about this week and weeks after this is that the last couple weeks, I don't know if you realized, the stuff we did was not that useful. I don't know if you realize that. Pretty mathy. What we're using now is actually really useful. And I'm going to start out with a business way of looking at things and how to make money. Maybe you guys don't care about making money, but someday you might. And that has to do with what happens if you have money to invest. And what decisions should you make about how to invest that money? Does that make some sense? So you might have $10,000 or whatever you've got, and you want a really good way of investing your money. Okay, one possibility is sticking it in the bank. And anyone know what the problem with sticking in the bank is? Any thoughts?
You lose equity.
What's that?
You lose equity. I mean, you lose not equity, but free money. You know, the access to your money without losing interest.
Well, you don't lose equity actually, and you don't lose access to your money for sure. You get as much access as you want with a bank. The issue is the interest rate is like 0.5% if you're lucky. Does that make sense? And you want to make money on your money if you can. So another way of doing it, which I'm going to pull up just for fun, and I want to talk about the issues with it, and that is, let me go find it, that one. Anyone know what that is?
Oh, yeah.
right? Hopefully you've seen charts like this and all this stuff, right? This is stock market. So the other way of investing your money is in the stock market, okay? And the average, around the average interest in the stock market is 8%, okay? Which is a whole lot better than a 0.5% that you get in the bank. What is the problem with investing in the stock market?
Risk.
Yeah, there's risk. Hopefully you all know it goes up and it goes down, it goes up and goes down, it goes up and down. Some years you get 12%, some years you get negative 10%. Now, when it goes up and down, because you get negatives and positives, you know, even though the average is 8%, what do you call that? How do you talk about it in statistics? How it's changing a lot in terms of your percent interest or percent returns.
Fluctuation.
It's our big word. You all need to know it because it's a biggie for the project.
Stratified, standard deviation.
Yeah, it's a standard deviation. So the standard deviation for investing in a bank is 0. You're going to get your 0.5% no matter what. It's not going to go up and down. It's just going to go 0.5% every year. Does that make sense?
Mm-hmm.
Standard deviation for the stock market is high. Okay, so we're going to make an assumption, okay, which isn't quite true, but it's not that far off. Let's just assume that the stock market is, say, normally distributed.
Okay.
And what you want to do is you want to say, let's suppose that the stock market is normally distributed, and let's say the mean is 8%. We'll call it, so that's 8 in terms of returns. And the standard deviation is 12%. So it goes up and down a lot, right? If the standard deviation is 12%. Negatives happen pretty often. So what is the probability that you're going to lose money in 1 year if you invest in one stock? So whatever your favorite stock is, whether you're going to invest in Tesla or maybe you're going to invest in Disney, whatever stock you have, if you just randomly pick a stock, then what's the probability that you're going to lose money? And the idea here, and this is what I'm going to unshare and reshare, is what we can say is that X is normally distributed with the mean of 8 and the standard deviation of 12. So I'm doing by percentages. Any questions on that?
No.
Okay, and what I want is I want to find out let me get here. What is the probability that X will be less than 0? Because you lose money means you end up with less than 0% gain. Is that clear?
Yep.
So as always, you should be used to this. You draw your beautiful normal distribution picture.
Mean is 8.
We have 8 as our mean. 0 is over here.
And 12 on the other side.
And what we want to do is we want to find out what this area is. Any questions on that? Okay, so this is a review, but it's an important review because we want to compare it with another option. Okay, so now what I can do is I can go and use my calculator. And let's do that, that one. So hopefully you all know, and you should follow along with me with your calculator. You can go to second distribution, and this is normal CDF. The lower bound will be negative throw in a bunch of 9s. The upper bound will be 0. The mean was 8. And the standard deviation was 12. And I paste, and I paste. I'm going to do this fast because it's last time. So you'll notice that there's about a 25% chance of losing money. Okay, now let's suppose that your idea here is that you have this money and this is your college savings. Okay, community college is cheap, but you're going to transfer next year. You're going to go off to university, and it's not so cheap. And you might have $10,000, and if you lose money, you can be dropping out of college. Do you think it's worth it? You have an average of 8%, but you got a 25% chance you're going to have to drop out of college because you had a bad stock year. What do you think? Would you do that? Or do you think you should just put it in the bank and then you'll be able to afford college no matter what? But you're not going to make a lot of money.
Put it in the bank.
Any questions? So what would you suggest?
Still 25% gain.
25% chance of ending up losing money, so you're going to drop out of college. That's what that is.
All right, 75% you're going to do something.
So Susie, Cecilia, Milgrass, Sally, what do y'all think?
I think there's a 75% chance you're going to get something good. So.
And 25%, it's going to make you drop out.
I will put it in the bank.
Yeah, I would put it in the bank. Okay, I hope that your college education is more important than having a 25% chance of just like losing it. Okay, yeah, but let me give you option number 2. Okay, so let me go to option number 2. And let me go back. And let me find it. There we go. Okay, let's suppose instead you put it in what's called an index fund. Okay, so this is the Dow Jones. You've heard of the Dow Jones. Okay, and what that is a collection of supposedly diversified stocks. And we're going to make an assumption that those stocks are independent, which is not the best assumption, but there's ways of dealing with that. And your other choice is to put it in a diversified stock, and where it's like a mutual fund that invests randomly into 20 different stocks. Does that make sense?
Mm-hmm.
Mm-hmm.
Okay. That changes everything, because now we're looking at not your returns from one stock, like if you bought Tesla or something, but now it's the average of 20 different stocks. Any questions on that?
Mm-mm.
So now let's take a look and do some math. Okay. Let me go to that guy. So first thing, we no longer have an X. Now we're going to be looking at X bar. We're looking at the average and not an individual stock. Is that clear?
Mm-hmm.
So it's now X bar. And that will also be normally distributed. And what the central limit theorem tells us is the mean will be the same, which in this case is 8.
Mm-hmm.
But the standard deviation is no longer 12. It'll be 12
Over
divided by the square root
20.
of our sample size, which is 20 stocks. Any questions on that? So what we say, let me write this out, is that mu sub X bar is still mu. That doesn't change. So what we say is the mean of the sampling distribution. So we look at all possible samples of size 20, and we look at the mean of the means of that, and that's the same as the mean of the population. But then if you look at a sample size 20, take an average, and then look at another sample size 20, take an average, and keep going with all possible samples of size 20, you get a lot of averages. And that's a bunch of numbers. And you can take the standard deviation of all those numbers. That is called sigma sub x bar. And the theorem says that is equal to sigma, which is your standard deviation of just a single variable, divided by the square root of the sample size, which we call n. So that's how I got that 12 over root 20. Any questions so far? Okay, our picture is going to look similar, except our calculations will be different. So let me go and do a calculation. So I'm going to go, and I'm going to go second distribution, normal CDF. Same lower, same upper, same mean. But now my standard deviation is no longer 12. It's 12 divided by the square root of 20. Any questions so far? And then I pop it in. And look at the difference. Do you think it's worth the risk now?
Yes.
Mm-hmm.
Now we're looking at 1 in 1,000 chances of losing money. So now you have the choice of going to the bank, popping it in, and getting your 0.5%, or you can stick it into a diversified fund of 20 investments, 20 stocks, and then you will make 8%. But there is a 1 in 1,000 chance that you'll end up losing money. Okay. By the way, this is how banks make money. They take your money that you stick in, and they make a lot of money off of it. Okay. If you ever wondered how they make their money, but that's how they make their money. Okay. Sometimes they loan, sometimes they invest. Okay. And my guess is that some of you put your money into a bank. It's a very bad idea, actually. You're much better putting it into diversified investment. Okay? If it's not diversified, this doesn't work, by the way. So that means that if one goes up, the other is not any more likely to go up or down. It's a different kind of. Any questions at all on this? This is called the central limit theorem.
Well, I have a question, not so much directed towards the central limit theorem, so sorry if this is a little off base, but it is related. One thing I've never understood about these mutual funds is that couldn't they all do poorly? Or if one goes up and one goes down, don't you end up exactly where you started?
That's why you have to have one that has a very strong diversification.
Okay.
If you have very strong diversification, so that's international, for example. So it needs to be invested in many different kinds of things, like real estate, international, because it has to be independent.
Okay.
So you usually get a smaller percent on average, but it's worth it if you're looking for a less risk.
Okay.
What I'm not going to do is tell you which one to invest in because you might lose, and I don't want to do that. You still got 1 in 1,000 chance, right? But I will tell you that I have invested wisely. And I've used statistics, and I am comfortable, let's put it that way. I don't spend very much, but I definitely am much more comfortable than most people that I know, and anyone that I know that teaches. Okay, and that's because I use statistics. Okay, but you have to understand it.
Standard, what's this called again? Central what?
Central limit theorem.
Limit.
It is the biggest statistics theorem there is in all of statistics, undeniably. You ask anybody in the world, they'll tell you central limit theorem is the biggie. And it says a few things. So let me go back and reshare. That would be that one. Okay, so the first thing is that the mean sampling distribution doesn't change, it's the same as the population. The mean, the standard deviation of the sampling distribution is not the original population standard deviation. It's reduced by a factor of root n. So it's sigma divided by root n. So that means if n is large, you get a very, very small standard deviation for the sampling distribution, which is the distribution of all possible sample means. Any questions on that? Okay, so, there's one more piece. Over here, I said, we're assuming that we have a normal distribution. Well, most of the time, just sampling, you're not going to get a normal distribution in terms of the population. And that's a problem because, again, if you don't have a normal distribution, there is no button in the calculator saying find the probability of I don't know distribution, right? Right? There's no I don't know CDF function. There's only normal CDF function. Is that clear? So when you do calculations, this doesn't work, but there's a very, very important piece of the central limit theorem. And let me type that out because it's that important. So important, I'm going to type it in red. So if the sample size is large, in our class, we're going to be saying large means greater than 30. Where have you heard greater than 30 in our class before?
In our project.
In the projects, okay? That was a subliminal message, so you'd remember it forever. So if the sample size is large, that means greater than 30, then the sampling distribution is approximately normal. Okay. If it's not greater than 30, you don't get normality unless the original distribution was normal. So you'd have to assume the original distribution is normal, then you're still normal. But that's a big, ugly assumption. But the idea is if you have a sample size, like you do on your projects, you have a normal distribution for the sampling distribution, not for your sample, but for all possible sample means. Any questions on that idea? That's really, really important. So if you have a small sample size, basically you can't do anything. Okay? So this is for quantitative data only. Notice we got things like mu and sigma. That's only when you have quantitative data. Is that clear? So what if you have the yes-no question? How do you deal with that? Well, one way is the binomial distribution, but it turns out that if you have a large enough sample, not greater than 30, that doesn't work anymore. But if your number of expected successes, or yes answers, and the number of expected no answers is bigger than 5, is what we're using in our class, then the sampling distribution is approximately normal. So let me write that down, because it's that important. For the yes-no answer, yes-no question, if the number of yeses, expected number of yeses, and expected number of no's is bigger than 5, then the sampling distribution is approximately normal. But we need more than that. We need a mean and a standard deviation. So just like before, we had mu sub x bar is mu and sigma sub x bar is sigma over root n. Now we have a different formula. So now we're not talking about mu's and sigmas anymore. We're now we're not talking about x bars anymore. We're talking about proportions, p's. So now we're talking about p's. And what we can say is that what we're going to say is mu. Unfortunately, we can't use Greek letters for P. Who knows the Greek letter for P? The hint is you all know it.
Z.
What's it called?
Phi.
Pi. And that's a problem because you don't want to use pi as a letter, as a variable. Do you agree?
Mm-hmm.
That's as confusing as it can be because you think about 3.141592656, et cetera, et cetera. So instead, we don't use pi. What we use is P for the population proportion and P with a little hat on top of it, which formally is called P hat for the sample proportion. So the mean of all possible sample proportions is equal to the population proportion. That makes some sense, right?
Yeah.
Standard deviation for the sampling distribution for proportions. This one, you're just going to have to trust me on, is the square root of P times Q over N. Okay, now we haven't seen Q before.
What's the Q stand for?
Huh?
Oh.
That's what I'm just talking about. What is Q?
What's the Q stand for?
So I'm about to type it out. I promise.
Okay, sorry.
So where Q is equal to 1 minus P.
Jumping it. Okay.
So the idea is if P is, say, 0.8, that means you have an 80% of the time people say yes. Then Q will be 0.2, and that's the percent of time people say no. Does that make sense? So P is a proportion of yeses, Q is a proportion of no's. And since they have to add up to 1, Q is 1 minus P.
Okay.
Any questions at all? Any questions at all on that? Okay. So we know we have a normal distribution. That's good. We have a mean. We have a standard deviation, which means you can start answering questions. Is that clear? You can start using this in the real world. Is that clear to everybody? Okay, so how would you use something like this? How might you use this information with the proportions in the real world?
If you were running for a political party, find
Right.
out.
Mm-hmm.
Yeah.
Okay. Any kind of survey with a yes/no question, we can use this. Okay, so for example, let me pop something in. Just 1 second, I have to get it in there. And let me find it. Right there. Okay, so Gallup is one of my favorite because you can actually get the numbers that they pop in. Okay, so U.S. opinion on Pence remains divided. Okay, so the question is, does it look like it really is divided? I think that fewer than 50% of the population of the United States likes Pence. What do you guys think? So here's what we've got. Americans remain as likely to view Pence favorably as unfavorably. Okay, so I think that fewer than 50% view Pence unfavorably. That's my thought. What do you think?
Yeah.
Okay, now do they really know? Do they really know that Americans, all Americans, view Pence unfavorably as 42%? They can't know that, right?
No.
How do I know they can't know that?
Because it's a sample.
Right.
They haven't asked you.
Yeah, they didn't ask me. They didn't ask me, which means they don't know, right? But here's the thing. With this 42%, do we know that it's fewer than 50%? Is that clear?
Yeah,
Is
that's
that
clear.
because of the small standard deviation?
We'll find out. We're going to do some calculations. We're going to calculate it. Does that make sense?
Mhm.
So here's what we're going to do. We're going to say, well, let's suppose it was 50%, okay? Then if you did their sample, what's the probability that you're going to get 42% or less? Does that make sense?
Yeah.
Okay, we need one more piece of information, which they always put in the bottom, hopefully. I didn't look at it, but they always do. So, where is it? You say it's there.
You must
Otherwise, I know what they always use.
survey method. You got to click on it up
Yeah,
above.
where was
Right
it?
there.
Survey methods, there it
Yeah.
is. Yeah, most people don't like it, so they hide it. So it's 1,035, got it?
Mhm.
Okay, so let me go to, let me write those down. So 1,035, what letter do we use for that?
N.
N, good. How about 42% or 0.42, what letter do we use for that? That's a little tricky.
Q?
No, not quite.
X or Z?
P hat.
Oh, P hat.
Because that's a sample proportion who said,
Mhm.
yes, I view you unfavorably. Does that make sense?
Mhm.
Okay. How about 50%, 0.5? What is that?
Wait, what?
0.5.
That's standard deviation.
No, that's P. Because I'm saying, well, let's suppose it's 50%. Now let's compute a probability. Do you see that?
Mm-hmm.
We're going to say if it's 50%, what would the probability be that you would get 42% for your sample? Any questions on that? Okay. So now I'm going to reshare my whiteboard. And I'm going to erase some of this. Let me go and... missed.
Okay, N is 1,035. P hat is, what was
That'll
it,
be in a minute.
43? And P is 40.
Okay. So now what we can do is we can put all that stuff in. So let me write down what we've got. So N, just to make it easier to write, I'm going to write it this way. N is equal to 1035. And then P hat, which I'll just write P-H-A-T for P hat, was equal to 0.42. And then we had P was equal to 0.5. I'm hoping you can all tell me what Q is right away if we know P is 0.5.
43. 0.43.
Q is 1 minus P.
0.5.
It's 0.5. 1 minus 0.5 is 0.5.
Oh.
If 50% say yes, 50% say no. Does that make sense?
Yeah.
That won't always be true, you know what I mean, in terms of we're not always going to have 50-50. Sometimes we'll have 80-20 or whatever. But in this example, we have 50-50. Any questions so far? Okay,
Yeah,
so now we can start calculating.
I'm confused on where the 0.5 is coming from.
Where the what?
The
0.5? Where the 0.5 is?
Yes.
Okay, so my thought was, I think that the question is, could it be that 50% of the population thinks of Pence unfavorably? Does that make sense?
Mm-hmm.
And the idea is we're going to see what the probability is of if you were to do a sample of 1,035 people randomly, such that in the population, 50% of the people would say, yes, I view Pence unfavorably. Then what would the probability be that you would end up getting 42% or fewer thinking unfavorably? That's the question. So
Does
that's
that
where the
make
0.5
it a
comes from.
variable?
What's
Because-
that?
Does that make it a variable? Because we're testing, this is sort of what we're testing.
We're seeing if 0.5 might be the true population, and we're going to see what's the probability that you would get something as low as 0.42.
Okay.
right? We're doing, well, let's just assume if it was 0.5, let's see what the probability would be.
Okay.
Okay. I know it's confusing, but we're going to spend the entire rest of the quarter doing this. So that's why I'm spending time on this. Okay. It's slightly different than what you'll get in the book, but it's exactly what you're going to get in the book for the next 6 weeks of class or so.
Yay.
So I figured we better do it. The book does a little of this too. Okay, so, and by the way, this is basically what you're going to have to do for your discussion post. So I want to make sure you're ready for it. All right, so now we go and calculate. I need my brush for that because it's too many Greek things. This is easy. Mu sub p hat
Equals P.
equals what number?
P.
But we have a number for it. It's 0.5.
Oh. Oh.
Yes, it's P, but now we actually have a number.
Oh, we have now a number. I'm sorry, yes.
And then sigma sub p hat, that one's messier. It's not any harder, but it's messier.
P hat.
Is the square root
of P
of 0.5.
0.5.
That's P times 0.5. That's Q.
Yep.
Over 1,035.
Yep. That's clear.
Takes a while to write it in on a board. Okay, any questions so far? We want a probability. We want the probability that if you were to do a sample, like what was just done, what's the probability that you get less than 42%? So we want the probability that p hat is less than 0.42.
Mm-hmm.
Any questions so far? Okay, so then what we do, and you should be used to this, we draw a little picture. We know our mean is 0.5.
Yep.
Because that's what it says, mu equals 0.5. And then we want the probability that we're less than 0.42.
That's true. That's true.
Any questions on that?
No.
All right, well, we can do it with our calculator now.
Yep.
So let's do the calculator. Let me go to the calculator. So now I can go and, as you can guess, I am going to go to second distribution, normal CDF. We know the low is negative 9999, it's less than 0.42.
Yep.
The upper is 0.42. The mean is 0.5. And the standard deviation was the square root of 0.5 times 0.5
over 135
divided by 1,035.
Right.
Any questions so far? Okay, then paste. Pop it in. All right, so is the probability 1.3?
No.
No, it can never be 1.3. How do you read your calculator?
It can't be over 1 because the whole thing is 1.
Right. Is the calculator making a mistake or are we confused?
We need to back that decimal point up 7 spaces.
Exactly. When you see that E-7, it means move it over 7. The first time you move it, it goes next to the 1. The other 6, you're going to get zeros.
Mm-hmm.
So then we can answer the question. So this probability was about equal to 0.12345 and a 1. So what do you think? What can you say? Big chance, little chance?
Really low.
Little chance. So very small chance. What was our one assumption that we had, by the way?
That it was less than 50%?
Yeah, the population was 50%. So what that says is it's probably not true. You see that? This is how we use the central limit theorem.
So the guy lied.
No, I lied. Not the guy.
No.
I lied.
I know. Well, I was just saying the person who would think that.
I mean, I'm a guy, so I guess you're right.
Yeah.
But I wanted to show you how you use the central limit theorem and how you use sampling and statistics. And this is how you use it. I should note, by the way, don't do this on your project. This is too advanced for the project.
Thank goodness.
Okay.
No offense.
But you want to hear the bad news if you think thank goodness?
I did.
Project 2.
Project 2.
Yeah, Project 2 is going to be all about this and more. But by then you'll have it all down, hopefully. But Project 1, you don't do this. You do your charts, you do your statistics, you talk about it, you make recommendations, etc. But for Project 1, that's all you do. This is post that. Any questions? Who's lost? Because this is kind of tough. Anyone lost? Susie, Milligras, Casey, Eric, Cecilia, Natalie. A lot of people came in when I wasn't looking.
My audio was breaking up for a bit, and so I am a little bit lost about what this p hat is.
Okay, so the idea here is, if you think about what we use for quantitative data, remember, we use mu and sigma, right? Mm-hmm. We use the Greek letters. So it turns out the Greek letter for p is pi, which is a dangerous letter to use because pi has a special meaning, right? Mm-hmm. So unfortunately, we can't use it. So instead of using pi, what we're going to do is we're going to use p hat for the sample, p for the population.
Ah, thank you.
Yeah. And 25 years ago when I first started teaching stats, they used pi. And I'll tell you, everybody was confused. So p hat is still a little weird, but it's not as bad as pi.
Okay.
Yeah, no one writes 3.14 when they see p hat. Any other questions on this? Any other questions? Okay, so again, there's one thing I didn't check and I needed to. What is NP? In other words, what are the number of yes answers that you would expect? And that's quite easy because it's 0.5 times 1,035. So let me type that in.
I've learned 17 of them, so that's half. Pretty much.
So NP, whoops, have to hit that one again. I missed it. One more try. NP is equal to 1035 times 0.5.
Which is 517.5.
Which is 517.5.
And if a thing is 135, that's exactly about half.
Right. So the big question is that bigger than 5? And yes, 517.5 is much bigger than 5. Is that clear?
Yep.
And then we should also check, which will be obvious, but I should do it anyway, NQ. That is equal to 1035 times Q happens to be 0.5 also, which of course is going to still be 517.5.
It's still greater than 5.
And that's still greater than 5. Okay, and 5 is a rule of thumb, by the way. Okay, just like 30 is a rule of thumb. Some people use 10. 5 is like sketchy, but we're going to go with it. I think that's what the book uses. So it's like maybe 2/3 of the books will use 5, and the other 1/3 will use 10. You probably want even more. Does that make sense? It talks about how accurate you are in these calculations. So with NP and NQ greater than 5, what that means is I was allowed to use the normal CDF button on my calculator because I needed normal. Is that clear?
Mm-hmm.
Just like in the other example, our N, in that case, was smaller than 30, we had to assume we had a normal distribution. With a yes-no question, you can never assume you have a normal distribution. Okay, because it's a bunch of yeses and nos. So you have to have, if you don't have NP greater than 5 and NQ greater than 5, you can't do this, period. Is that clear? Mm-hmm. There are more advanced math ways, and I'm not talking about them in this class. Sound good? Mm-hmm. Any questions so far? Any questions? Okay, I want to give you one more example. This is going to be a business example. So let me kill this guy. I want to do a little bit of calculation for the example first, but I have no more space, so I have to do this. Gone. Okay. Let's suppose you're in business. I didn't ask anyone in business here. Any of you guys business majors or interested in owning a business someday?
Did own one.
You did own one. Okay, so you've been in business. Okay, at the end of the day, you don't really care that much about how much the average customer spent. What do you care about?
If I made more than I...
Right, you look at your cash register, and it's not the average amount per customer that you care about. It is...
what I made.
Yeah, how much money the customers gave you. Does that make sense?
Yes.
Mm-hmm. That's what you care about. That's all that matters, isn't it? Okay. There's also how much you spent, too. But we're going to stick with the revenue side right now.
Okay.
Is that clear?
Yes.
So we're not interested in the average. We're interested in the total. So the first thing, any of you remember the math symbol for total? Anyone remember the math symbol for total?
Is it the sum sign?
Yep. Do you know what you call that?
No, it just looks like a sideways Z.
That's what you're talking about, right?
Uh-huh.
Epsilon.
Okay. Here's the bad news. It's called sigma. But it's like English. We have capital and lowercase. This is capital sigma.
Okay.
The other one we'll be using is the standard deviation one, that's lowercase.
Okay.
So if you want to look at sigma sub, sorry, you want to look at, not sigma, just 1 minute. I had typed it wrong. One more try. If you want to look at the mean of all possible sums, that's going to be mu. Instead of sub x bar, it's going to be sub sigma.
Oh, okay.
Sometimes you say sigma x, so maybe I'll do that just for fun. Because it's the sum of x. And this is actually pretty easy. Because if you think about it, if you know what your mean is, your mu, how do you get your total?
Add them all up.
Yeah, but that's the mean. You know your mean. How do you get your total?
I think you would multiply by the number of figures you calculated.
Yeah, we have a letter for that. Do you remember the letter?
No.
It's easy.
So you say...
mu times n.
Oh, yeah. That's
And what's your sample size, right?
Yeah.
Take your mean, multiply by your sample size, and that gives you your expected total. Any questions on that?
Nope.
Okay, now I'm going to do something that you're all going to love, because it's math, and you love math, right?
Oh, we love it.
Okay, let's do the same thing. Remember, sigma sub x bar was sigma sub x bar was equal to sigma over root n, right?
Mm-hmm.
Oh, yeah. Mm-hmm.
But I need to multiply by the total. Are you clear with that?
Mm-hmm.
All right. How many of you remember how to rationalize a denominator?
Just divide it. I mean, well, multiply by both sides since it's...
Not both sides, actually.
Multiply the numerator
By what?
by whatever you want gone in the denominator.
Yeah, root n. But if you're going to multiply the numerator, you also have to multiply the denominator, right?
Yeah, that's what I meant.
It's like a 1 then.
Yeah, that's what you do. You're always allowed to multiply by 1.
Mm-hmm.
So that's sigma times root n times n. What's the denominator become? I have a root n times root n.
1.
The denominator in root n times root n is not 1.
Oh, root n times root n. It's root n squared.
Which is very simple. It's not 1. It's n.
Squared.
It's n. The square root squared is just itself, right?
Oh, yeah, it is just itself.
Don't you love algebra?
Yes. Thank you.
And then these n's cancel. Got it?
Yes.
So what we get here is sigma sub, I'm going to call that sigma x. So standard deviation of all possible sums is equal to sigma times root n.
Right. Yep.
Any questions on that?
Nope.
All right, I want to let you know, when I give this on a test, not even half get it right. Okay, and I don't give trick questions. It's because they don't read the question, they don't think about it. So if I ask about a probability that involves a total, you must use these two formulas. Got it?
Mm-hmm.
If I ask you a probability about a mean, then mu sub x bar is mu, and sigma sub x bar is sigma over root n. If you don't pay attention and don't read the question and see the word total or sum, then you're going to get it wrong. So do you think any of you guys are going to make that mistake?
Nope.
All right. So again, over half make that mistake. And I will tell you, I always ask questions about these things. Okay, definitely either or both, question about total and a question about means. Got it? And if you don't use the formulas, you will get it wrong, guaranteed. Any questions on that? Okay, so now we could do a question. We could do a problem. Is that clear? So let me pop one up. Second.
Type pretty fast, Dr. Green.
What's that?
You type really fast.
That part? No, I'm copying and pasting.
Oh, okay.
I'm a fast typist, but this is copy and pasting. And I got one more piece to copy and paste. Okay. So suppose that the number of hours per month that college students volunteer is normally distributed with a mean of 2.8 and a standard deviation of 6.7. Is it clear so far? Okay, for the following questions, do all the following. Write down the indicated distribution, sketch the appropriate diagram, answer the question, state whether the normality assumption is needed. The question is, find the IQR for the sum of 15 randomly selected college students volunteer hours. Any questions on the question?
No.
Okay, so the first thing, if you read this, it says write down the distribution. What that means is we need to write down the following. There. So we need to say, first thing, our distribution, what we're interested in is sigma x. It's a sum, and sums are sigma x's. Is that clear?
Yeah.
Okay, then we could say normal. The mean, now I can use my text instead because I think the rest is all going to be, at least the next part is. The mean was 2.8, but we need to multiply it by the sample size because that's what the formula says. So 2.8 times 15. Any questions so far? The standard deviation was the original standard deviation, which is 6.7, and then times, and now I'm going to have to brush it because there's no square root piece in the brush, in the texting, times the square root of 15.
Right. Now we can go to our calculator.
Any questions on what just happened? Okay, so we just wrote down the distribution. Now we need to sketch the appropriate diagram. Any questions on that?
Nope.
All right, so let's sketch the diagram.
Bell curve.
And I hope you all know how to sketch by now. Let's see if I have room. Hopefully I do. Okay. By the way, 2.8 times 15. It's nice to calculate that one. Is, oops, missed. 2.8 times 15 is 42.
And that's our mean.
There's your mean. Okay, we want to find out the IQR. Now, if you remember the IQR, that is between what percentile and what other percentile?
Between 25 and 75.
Yeah, 25 percentile and 75 percentile. Any questions so far? So we know that area there is 0.25. And we also know that the green area, which I'm about to draw, is 0.75.
Yeah.
Any questions on that? Okay, we need to find the values of sigma sub x. So obviously, you're not going to want to do this by hand. Let me write down a few things. So we have 42, comma, 6.7 root 15 was our normal distribution, and we want less than, we want IQR. So now we go ahead and use our calculator. So again, slow me down or stop me if you don't understand something. So I'm going to go to, again, distribution. What do I use this time?
Oh.
The inverse.
Inverse norm.
Yeah, this is inverse norm because we're given the area and we want to find the value on the horizontal axis. The area, let's do Q1 first, 0.25. Our mean was 42.
What was the mean again?
42, you should be able to see that. Our standard deviation was 6.7 times root 15.
Two point something.
Okay, I don't care. I'm just putting it in.
I know.
Let the calculator handle it. I don't care about the tail. Can I hit paste? Everyone good?
Yeah.
Okay. And there we have it's 24.5 to 1 decimal place, right? And then I do the same thing.
For the other one, okay.
I do inv norm with changes this time.
75.75.
0.75, and everything else is the same.
59.5.
Yep, 59.5. Okay, so the IQR, there's kind of two ways of writing it. One is the IQR is between 24.5 and 59.5. The other is subtract the two numbers, and you get an IQR of 35. 59 minus 24 is 35. Any questions on that idea?
Nope. Anybody else? Nope.
Okay, but we're not done yet. So let's write down, let me write down the answer first. So the IQR is equal to, I'm going to write 59.5 minus 24.5, which is equal to 35.
Yep. And that's what you want as the answer, the whole thing, or just 35?
I liked, well, on a test, I like the work shown.
Okay.
Okay, then it says, is the normality assumption needed? Yes or no?
I think yes.
And of course, I want more than a yes. I want why is needed, why it isn't. It has everything to do with right here. What's that number? 15. Why is that important?
It's less than 30.
Yeah. This is quantitative. Remember, if it's a yes-no question, don't even think about the number 30. But we can say right away, that n is equal to 15, which is less than 30. So the normality assumption was needed. Okay, in the real world, it just, what that means is that that's not good because that assumption is probably wrong. So you shouldn't even be doing it. Does that make sense? In the real world, what that really means is, hey, you better sample at least 16 more people.
Yeah.
Okay, is that clear?
Yes.
If you don't sample them, then this whole normality assumption might be wrong, and all your calculations could just be wrong. And for scientific evidence, you don't have any. Does that make sense? Okay, because that assumptions are bad. Whereas if you're greater than 30, then you have no assumptions needed, and you can just do it. Any questions at all about the central limit theorem and using it for sums or means or the yes-no question? Any questions? Okay, we're finishing a little earlier. Again, we got a project due, so I want to give you kind of, work on your project. Note the yes-no question one, the proportions. That is basically the model for your discussion post or discussion reply for this week. And I gave a model also on the discussion board itself. But just note, it's a little confusing. And hopefully that will help you out. Any questions at all on any of that? All right. So you know what I get to give you now?
Secret word.
Secret word.
Eric and Dan, don't leave, thanks.
The secret word today
Sedan, I mean.
is normal. Because if you don't have a normal distribution, you can't really do anything. But if you have a sample size that's large enough,
There's no
n greater than
assumption.
30 for the quantitative, or NP and NQ greater than 5 for the yes/no question, and the central limit theorem tells you that you have a normal distribution. So that's the main thing. Again, I don't go over every little detail in this chapter, but these are the main points. And so you definitely need to watch the full video and read the chapter and all that and do lots of problems. So are there any questions? Let me go to this screen. Are there any questions about anything? This is your chance.
Sally, you wanted us to stay over?
Sorry, I can't hear you.
Sally, she asked for me to stay.
Yeah, are you going somewhere?
No, here.
Okay. Well, we're going over this with him first. Can you not close the webinar? We can stay in here and talk, or?
Yeah, I can talk to you a bit.
No, I mean,
After.
us.
Yeah. I can stop the recording if you want.
Yeah.
Any other questions before I stop the recording?
I do. I have one more question about the thing. So the standard, I mean the central. Oh man, I forgot the name of it already again.
Central limit theorem.
Thank you. Central limit theorem. Is you expect that to use to find out if we sampled enough people for our question, yes and no, on our project?
Well, remember you had to get over 30, right?
Yeah, well, which we did.
So you did. You're not using the central limit theorem.
Okay, good.
The over 30 in your project was subliminal.
Okay, got
So
it.
that you'll never forget it. Got it?
Got it.
Okay. Because hopefully you've learned over 30 is the requirement to have a good study. Does that make sense?
Yep.
To have a great study, you usually need over 100. That's for quantitative. For the yes/no, we'll do this next week. It's typically over 1,000.
Wow.
Wow.
Yeah. And that has to do with something about next week going on. So that's the main reason. There's a lot of reasons, but one of the reasons why I don't let you have yes/no questions in either project 1 or 2 is because you don't want to have to survey over 1,000 people.
Oh, no, Morgan.
No, you can.
Other questions?
Yeah.
Hurry up, get it done.
Any other questions? Again, as always, if you don't have questions, you can say goodnight.
Good night.
Thank you.
Okay.
Weirdo.
Look, what was that?
You need help?
Look at that.
And I'll stay on until there's no more questions.
Practically removed a tumor.
It was on your face.
Okay, so good night, Casey.
Restart you.
Andrew, turn your mic off. Okay.
Good night, Cecilia. We still have a bunch of people, so I'm waiting until it at least gets sparser. Any other questions? So again, if you don't have questions, you should probably say good night. Any others? All right, I think I'm going to stop recording. But thanks for watching. Those who are watching this as a YouTube video. Don't forget the project is due on Sunday. Don't wait until Sunday to do your project. Your goal is to turn it in on Saturday. So if something goes wrong, you're fine. Because I'm not going to give you an extension. So again, do it early. And if you can send your rough draft to me in the next 2 days, that's best. Maybe even Thursday morning is fine. But after that, I have a very long day Friday. So I'll have no time on Friday because my office mate's back in prison, which means I got to teach pretty much all day on Friday. And then I'm going somewhere in the evening. So don't expect much of anything on Friday in terms of long reviews. So I'm going to hit the stop recording.
Cut all that.